I want to talk about information extraction from visually rich documents. And specifically, I want to survey and compare a little bit the latest ideas in this field based on transformer models with a slightly older approach, graph neural networks. So to start with some motivation. So my first point there says business communications happen in human readable formats. Okay, so this might seem like an obvious statement, but I think maybe for a time traveler coming from the 90s, this might actually be a bit surprising, right? At least if you were like an XML enthusiast, you might imagine that at this point machines are talking to each other directly with some standardized formats. This is not really how things work. Maybe our time traveler, if he was a bit cynical, might even say that, okay, in the end, digitalization just means PDFization of processes. But yeah, so the truth is, I think it's hard for machine-readable data exchange formats to catch. So while researching for this presentation, I learned there is actually a EU directive for electronic invoicing. I didn't know about this. I don't know, maybe some people here heard about this, and I don't know, maybe it's even in place used in some places, but also doesn't seem to be something you can just pip install, right? And if it were, I don't know if it would be a good thing that you have to be a programmer to issue an invoice. So it's just natural that people work with documents like this, a PDF file or whatnot. And we just need tools for intelligent document processing. All right, so just to define a bit what I mean by visually rich documents or documents with layout, here are some examples. There are many relevant types of documents like this in various business types, right? So invoice and receipts. Well, technical documents like this tend to have lots of tables, financial reports, forms that you fill in, right? The main characteristic here is that this is not just text that makes sense as a sequence of words, right? The visuals of the document and the organization of the text conveys meaning as well. All right, so then what is information extraction and how would it look like in practice, right? So what we want is, given a document like this, our invoice, we want some system that can turn this human-readable document into some machine-readable format, right? This would be, say, an object or dictionary like this with specified fields, say in the case of the invoice, sender date, invoice number, or even some more structured elements like line items, right? So these individual things listed here, those are line items, and to our invoice corresponds a list of such things, and then each item again is a structured little thing, right? Which has, say, a description, a quantity, a unit price, and so on, right? Okay, so that's what we want to do. Now, if we're always processing invoices from a fixed vendor with a fixed layout, then you can just code up something that knows where to find things, and right, you can do this extraction by pure logic, so to speak, normal code. If you want to have a more flexible system that just receives any old receipt, more or less creative in the layout, and can do this job for you, then this becomes too complicated. You need some form of learning. Okay, so then just to give an insight into how such an AI system works, there is this important intermediate step where you identify in your document so which words are interesting and what they tell you, right? So our AI system, or our language model would take a document and say, okay, so here we find some sender name, and this here is a invoice number, here is a date, this column here is giving us quantities. And then the step going from here to our structured data, this is typically something you do then with a more normal program, right? Like we implement the logic that does this. And yeah, so then we get the exact format we want. There may be some extra pre-processing step, like if we know the quantity is a number, then we can do something to ensure that we get a number in the output, and so on. Okay, then with that out of the way, what I want to talk about for the rest of the talk. So give an idea of these two methods used for document understanding, graph neural networks and transformers. And then I want to show you some comparisons. And I'm especially interested in this low data regime where we have training data, but it's maybe not too much, or we want to just not have to gather too much data. I say low data regime a bit in opposition to few shot learning. I really don't mean we want to learn from 5 examples, but maybe from 50 or a couple hundred, something in that ballpark. All right, so then gets to the graph neural networks. So what's the idea? So a graph neural network is just a machine learning technique which can process data organized on the form of a graph. So a graph is just a picture that you made of dots and arrows joining the dots. So it's just the black stuff in this picture. And then typically we want, in addition to just the graph itself, we want some extra information. So we want to associate it to each node some vector of numbers. And then to each label, to each edge or arrow, right? We want a label that just belongs to one of some number of fixed categories. And what we might expect out of our system is to classify the nodes or vertices, again, into one of L fixed categories. Okay, so one simple example, maybe this graph represents some people and financial transactions that they made. Okay, so then maybe in this case, our labels for the edges would be, okay, was this transaction in cash or card? These vectors are some information we know about those people encoded in a numerical form. And what we might expect as output is a classification of these users as legitimate users or possible fraudsters or something like this. Okay? So this is one simple idea. Now, what does this have to do at all with documents with layout? So the idea is, because it doesn't really make sense to linearize this text as a sequence of words, we create a graph that encodes the structure of the document, right? And so the idea is, in our graph, each node represents a word in our document. And then for each word, we look at this quadrant, the stuff above, below, and to each side. And then we look at the nearest neighbor of this word in each direction. Those are also nodes in our graph, right? So then we add an edge connecting those nodes, okay? And then we look again at these neighbors, the neighbors of the neighbors, and so on and so forth. So you keep going like this, you cover the entire page, you get a graph. Okay, and then here's an overview of how a machine learning model for visually rich documents can look like. So we have a page, we look at the words, we make this graph. Then, remember, for each word, which is a node, we want some numeric encoding of that word, right? We can use a convolutional layer to look at all the characters and basically understand what that word is. We also have the location of the word on the page. Those are some numbers that we can collect. And if we're feeling enthusiastic about this, we can even think of maybe some patterns, some handcrafted text features, right, that our word matches or not. And yeah, so those are the features we collect for each word. Our edges are labeled by the direction they point at. Can be, then a neighbor can be in up, down, left, or right direction. And then we feed this information, this graph, through a GNN block. I'm going to talk about this in a minute. We have some blocks, maybe 5 of them. And then at the end, we stick a very normal linear classification layer. And then we can expect at the end to classify each word as one of these categories. Right? In the case of the invoice, would be sender, invoice number, date, or even say, okay, this word is not so interesting. You can ignore it. Okay, yeah, so this is how our system looks like. So now looking a bit in more detail inside this GNN block. So this is my most technical slide, so if you can't follow this one too much, then I'll be back in 2 minutes. But so what does the GNN block does, right? So it receives, as I said, this graph as input, and what it does for us is it returns to us a new graph that has exactly the same shape, the same edges with the same labels, only these feature vectors changed, right? Okay, and the way I compute the feature vector of, so, okay, let me put it like this. You can think of each node here as passing a message to its neighbor. Okay, through these arrows. So this guy passes 1 message, this guy passes 2 messages, and the message is based on the feature vector of the node. Okay? Or if you focus on the receiving node, right? So say, how do we compute this feature vector for this guy? So it's this node here, right? So what we do is we look at all the incoming edges, and then we look at the source of that edge. That source edge has a feature vector associated to it. Then we multiply this by some weight matrix, which is learned. And this weight matrix depends also on the type of the edge. And then we just collect all these quantities, these messages, we collect them together, okay, with this summation. And this, then we apply some nonlinear activation function, and this is the output feature vector of this one node. Okay? Yeah, so that's the basic idea behind it. So just to show you how, well, this is a natural idea. Yeah. So the interesting thing about what I showed you, this GNN layer, is that it takes as input graphs of any shape, right? An arbitrary shape, it can work with it. But if I fix my graph, then this formula from the previous slide recovers some well-known things, right? If my graph is just a sequence of dots on a line, right? They have this structure, and then I connect each node with, say, the 5 nearest neighbors, and I label the arrows by the displacement, right? So I have these incoming edges here, but I also have a similar structure for each of the other nodes. Then that formula exactly recovers the convolutional layer, okay? Can also do this in 2D with a similar graph. Yeah. So if my graph is a complete bipartite graph, meaning I have some nodes on the left, some nodes on the right, and everybody on the left is connected with everybody else on the right, and each edge has a unique label, then, okay, this is just a fully connected layer. And as a last example, if I have a complete graph, so every node is connected to every other node in both directions, but then I modify the message passing a little bit such that instead of just summing up, so this guy receives some messages, right? Instead of just summing up all the messages with essentially the same weights, this summing is weighted by relevance, where the relevance is calculated by some bilinear product of the features of the incoming and receiving node. Yeah, and that's the transformer layer. Okay, yeah, so I think that's it about graph neural networks. Now an overview of the transformer method. So, yeah, so transformers were introduced in 2017. And since then, most state-of-the-art NLP models use this kind of architecture. these models are very good at determining which parts of a sentence relate to each other and also modeling long-term dependencies inside a sentence or text. This kind of models really introduce this trend to make bigger and bigger models, and say, for instance, now ChatGPT is based on this. Transformers have been used now also in computer vision and other areas more and more, and there are also variants for visually rich document understanding. Okay, so these models are pre-trained on a large collection of documents, and so they are easy to fine-tune on many different types of downstream tasks. Okay, all right, so before I can tell you how these transformers for documents with layout work, let me just recap or give a quick introduction to the good old transformers for text. Okay, what's the idea? So we have some input text, and then we break it up into tokens. Okay, so these tokens are more or less like words, except maybe some word that is not known to the model might be broken up into sub-words. We also add a token for the beginning and end of the sentence. Okay, and then each of these tokens gets an encoding. It gets represented by some vector of very large dimension. I add some position embeddings, which are also vectors that encode the position of the word inside the text. And then I feed it through this transformer layer. And out of it come, again, a sequence of vectors of the same shape. Okay? And these encodings are just they have some information about this token, but with more context, right? So and then we can do whatever we want with these encodings. So maybe if we want to classify the sentence, maybe do some sentiment analysis or something like this, then we can ignore everything else and just look at this encoding of the beginning token and do some linear classifier on top and try to train this for our task. If we want to do part of speech recognition, so say figure out what are the nouns in here, then again we do some linear classifier over the corresponding token encodings. Okay. Now, what I really want to emphasize here is that the transformer transforms a set of inputs into outputs. It's not really a model for sequences. Okay? And that's why we have to stick in this position encodings by hand to break the symmetry, so to speak. Okay? And this is what's very good for us, because our documents with layout, they don't have a preferred linear ordering of the words. So it's good that we have a model that intrinsically only cares about sets. Okay, so here is then a picture of one transformer-based model for documents with layout. Maybe this is too much detail, but just to give you some, and I just took this picture from one of the papers. The basic idea is then to replace this position embeddings with bounding box information, right? So here, these things here in the diagram, they are the token embeddings of the words in our document, and then they added, they actually add some 1D position encoding from some linearization of the text, but important, there are now these 2D position encodings, which just tell you where the bounding box of that word is. And then some of the fancier models also break up the image of the page into patches and then do some encoding for each patch and also feed it through the model, but this is kind of an optional step. And then feed it through the transformer layer, and then out we get this higher level encodings which we can work with again. That's the basic idea behind it. And, well, there are now several variations of this architecture available which already come pre-trained. So this layout LM model from Microsoft is one option. Then it has a multilingual variant. There's also this Bros model that I find very interesting. It's I think the simplest possible thing you could do, it doesn't have this visual backbone. It's just looking at the text and the geometry. Yes, so that was for transformers, and now I can show you some experiments. So for these experiments, I'm going to use the SROIE benchmark dataset. It's one of the standard ones that everybody looks at. This is a dataset of cashier receipts. So it has 600-something training documents, 347 test documents. Yeah, and then I'm going to compare our GNN, this pretty much the diagram that I showed you some slides above, with browse and layout LM. And one thing to emphasize here is the difference in size. So our GNN has 2 million parameters. Browse, layout LM, these transformer-based ones have upwards of 100 million parameters. So yeah, so this one you can train on your laptop and run it on your phone. For those, you already need specialized hardware. And yeah, maybe another comment, another point to keep in mind is this is really an easy data set. It's kind of a boring one. There is not much natural language content in this. And yeah, and so this might maybe tell us that the pre-training and this fancy attention stuff is not as relevant as it might be. Okay? And then again, I'm really interested in what happens when I don't give myself too much training data. Yeah, so here's the first experiment. So again, I'm comparing the GNN model and then this transformer-based one browse, and without a visual backbone, and the layout LM, which is a transformer-based with a visual backbone. The first thing I do is I just train these models on all the data. So it's this column. I get this F1 score. Maybe it doesn't matter too much what the score is. It's just a comparison between it. And then I train, again, these models with half of the data. I get two experiments here, then a quarter of the data, and so on, right? And this is what I get. So what do we learn from looking at this, or what do I see that looks interesting? So when we give ourselves 9 training samples, well, sometimes we get luck and the model actually learns something, but most of the time it's just a random guess. We have 5 classes here, so 0.2 is the F1 score of a random guess. Then at some point, these models kind of start learning something, but we still have too much variance. So it's in this area of 100 to 500 documents that we start to get reliable results. Our GNN, which doesn't have any pre-training, it is slower to catch up and to really start to work. And in fact, even I think I see a trend here where probably this model didn't really stabilize. It would benefit from more training data. The other ones seem to already be pretty stable when you get to 500 documents. And the other interesting thing is that layout LM really does a very good job to learn fast, right? It has the steepest curve here. Okay, so then another thing I asked myself is whether this faster learning is due to the visual backbone, but looks like it is not, because if I just use a good old BERT for text, then it also has this characteristic. So I think the layout LM variant really just has a better pre-training. Yeah. And then the last point I wanted to show is about this handcrafted text features. I remember when I showed you this GNN model scheme, it's very easy to add, well, anything you want. In particular, you can just match your text against patterns and add features that say, okay, does it match or not? So I just try to compare what happens if you, okay, just don't do this, have no handcrafted features, or if you add, just recognize the word total, which is meaningful, right? So if you're looking for the total amount of a receipt, and then also a regular expression that matches a date. So that's the orange stuff. And then if on top of that, I also can add a pattern that matches a numerical amount, like a money amount. And yeah, in the end, this gives you, there's a little bit of an edge if you have these handcrafted features, especially here in this area of low training data. But in the end, the difference is tiny, right? It doesn't seem like you get too much from adding this stuff. Yeah, and then I think that's what I had to say. So I think just to summarize a little bit, we need tools for intelligent document processing. Transformers are the state of the art in this task, but GNNs of a much smaller size can still be competitive. So there might be places where they are a good choice. Yeah. And then that's it.
Yeah, thank you, Augusto. As well, this was a talk like bringing together some of the topics we've heard already today. We heard something about GNNs in the morning. We heard a lot about transformer models already. So thanks for that. And yeah, now we have our round for questions. We have a microphone here and in the back. So if there are any questions from your side.
Can you comment a little bit on this Thanks for the talk. Can you comment a little bit on these impressive F1 figures? Was that just, an accuracy on a per document level, or did you go into details for that?
Okay, yeah, so this is the F1 score on a word level classification, right? So if I maybe go back right to the beginning, I'm just measuring how well my system can reconstruct this picture. And yes, the scores are impressive, right? It's like 95%. But that's because the data set is kind of easy. And I think this is one of the problems in this area. There's not a lot of publicly available data, and yeah, the benchmark data sets they're okay for comparing different models, but they're not super interesting. Yeah.
Further comments or questions, maybe?
Is the data fed, I said maybe I missed this, as an image, like of the PDF, or the content of the PDF itself as latex? Or
Yeah, so the input is really the text. So let's put it like this, it's the OCR of that image. Yeah. So in this experiment, we don't care about the OCR quality, right? So it's just given as an input, and we assume, well, this is perfect.
so you're getting like a bag of text of the PDF?
Yes, exactly. It's a list of words with their corresponding bounding box.
I see.
Yeah.
From me. So you earlier showed, or like quickly illustrated, that the GNN can be equivalent to a transformer model as well. So is what you showed on this F1 model comparison plot really illustrating that the word embedding that you use in the other models is more powerful, or is there more to that plot?
No. So in my experiment, the GNN one, I'm not using this modified message passing,
Okay, I see.
which weights the relevance of a message based on who it came from. So this is not done, so it's a more naive variant. Yeah.
Okay. Then we can maybe finish here. We will take a 10-minute break, but before that, thanks again for Augusto for the talk.